that, James. Shall we kickstart the session?
Yes, let's do.
Okay. Yeah, I think our attendees have slowed down now. So yeah, if you'd like to start, James, please go ahead.
Great. Well, welcome to this session this morning on structural integrity and standards. My name is James Campbell. I'm from Brunel University, London, and one of the Brunel team based at NSIRC. Our first speaker today is Faris, who is a third-year PhD student from London South Bank University and speaking on inspection of corrosion under insulation.
Oh, I think I can't start my video as well. It seems like it says you cannot start your video because the host has stopped it.
Okay. Can you share your screen? That's the more important bit.
Yeah, so I share my screen now. So
right, we can see that.
Yes. Right. So I'm Faris. I'm in my third year, my PhD now, which is also towards the end of my PhD. So today's presentation is going to be focus on a bit of overview of my PhD project in general. So entitled Quantitative Data Analysis of Pulsed Eddy Current Responses for Pipeline Profiling. The main motivation is corrosion under insulation, or CUI in short. Is a very common occurrence in pipelines, and this type of corrosion, or CUI, is very difficult to be inspected due to the multi-structured layers of the pipelines, where we have a pipe wall being insulated with being wrapped with a layer of insulation and also cladding as well. And the use of conventional NDT methods such as UT or eddy current testing, those methods need the insulation to be removed. And our solution for this, or our NDT solution for this, is by using a technology called Pulsed Eddy Current. So a Pulsed Eddy Current system, Pulsed Eddy Current technique, actually belongs to the eddy current NDT family. It has the advantage of being a non-contact technique and can penetrate through multiple layers of insulation. So it has a very great potential in pipeline inspection. So the basic principle of a PEC system follows the same operating principle of an eddy current system, except that an eddy current system generally use sinusoidal wave as the excitation source, while a PEC system uses rectangular wave. So this slide shows us the basic experimental setup that we have developed. So a basic PEC system normally consists of a probe, an excitation circuit, and also a acquisition unit. So the content of the thesis, I would say, so can be divided into three. So into three parts. So the very first part is where I look at the probe performance analysis. So the problem that we are trying to solve here is that probe diameter largely affects PEC performance. So whenever we want to optimize a PEC performance, we try to optimize the probe parameters. But the conventional way of optimizing these probe parameters is very time consuming. So in such a way that the process of signal processing acquired from the probe will be processed by a certain signal processing process. And then this signal processing process involves determining pre-configured parameters. So whenever we change a probe diameter or probe parameter, we have to change the process of signal processing again. And this makes it very time consuming, and it makes it less likely to be automated. So we propose a solution to this by using signal decomposition method. which is a technique called PCA. So PCA or principal component analysis decomposes a signal set into features that explain the most variance. So so in basic principle, we use this by inputting a set of signals into the algorithm, and then the algorithm itself will then output values that quantify how separated the signals are with each other. As you can see from the figure here, we have a signal set, put it, and then we use that as our input to the PCA, and then from there we can quantify. At the end of the day, we get a graph that quantify the sensitivity of the pack. The second part of the thesis is called enabling in situ calibration. So the problem that we are trying to solve here is that the current technique of pack doesn't have a method to do in situ calibration. So in such a way that the conventional way, the conventional entity method such as UT and also eddy current still requires close contact with the pipe wall. So and the current pack signal interpretation requires calibration block. So at the same time, the technique is also not immune to lift off as well. So we get around this problem by proposing a feature extraction technique using the inverse gradient of the signals. So we first analyze the mathematical formulation, and then from there we discovered that there is the gradient or the inverse gradient is highly correlated with the thickness squared, or the square of the thickness. So this enables us to propose a calibration routine that can be carried out in situ in real life deployment. At the same time, this new feature that we propose is also immune to lift off. It's also immune to cladding thickness variations and also insulation thickness as well. The third part is optimizing feature extraction. So initially, with the proposition of the new feature, it requires determining two threshold values. So first threshold value is here, and second one is here. So we initially heuristically chose these two values based on looking at the signals that, based on looking at the portion of the signals that behave like a straight line. So this is rather unintuitive, not very intuitive, and then it also requires a bit of experiment to it. So in order for us to solve this, we propose the usage of optimization algorithm, which is a particle swarm optimization. So we first formulated this problem as a minimization problem, and then we solve it with PSO. And then as you can see from the figures here, the method is proven to be effective as compared to brute force method. And to conclude, we have developed a pack system that is capable of doing in situ pipeline inspection without the need for insulation removal. We have also looked at, in terms of the data analysis as well, a signal decomposition method, which is being used for probe improvement. We also look at a new feature. We propose a new feature that enables us to do in situ calibration. At the same time, it's also immune to lift off cladding and insulation variations as well. And the third and the last part is optimization algorithm for signal processing improvement. And I would like to thank all my supervisors involved for helping me out through my PhD. And yeah.
Great. Thank you very much, Faris, for an interesting presentation. If anybody does have questions for the speakers, please do put them in the Q&A box on the you should see it in the menu at the bottom, and we can ask them also. The speakers will be able to answer any questions that we don't have time for. Are there any questions for Faris? Yinjin, yes.
So Faris, thanks for your presentation, very interesting topic. And so my question is that, we are talking about inspection of flows beneath insulation. So is this technique applicable to all types of insulation? As insulation material can be various made of various composition, and then how would that affect the signal of your inspection?
So we've looked at quite a number of materials. We've looked at quite a number of a wide range of tests. We've done quite a wide range of tests as well. So, but I think in general, what we look at is a non-conductive, non-magnetic layers wrapping the pipe, and then on top of it, a layer of cladding, like a very thin layer of cladding. So we look at that in our experiments. So yes, all of these all of these material properties, they affect the signals differently. So, but interestingly, our method, or our feature, or our signal processing method that we propose, managed to get around it. So it managed to compensate for all of these variations in the parameters. So yeah, that's my answer for that.
Okay, thank you. I had a question. You've said how the insulation thickness and things all vary the signal you get. For your technique, do you have an idea of the size of corrosion defect you could expect to practically detect underneath, or with the presence of insulation?
So for the scope for this project, we look at insulation layers of 40 mil, 30 to 40 mil, a cladding layer of 0.5 to 1 mil. And that also includes some aluminium, stainless steel, and also galvanized steel cladding as well. And then a carbon steel pipe. So the carbon steel pipe is 12 mil thick. The nominal thickness is 12 mil. And we managed to detect the wall thinning up to 4 mil. So I would say the corrosion levels is 8 mils of corrosion. We managed to detect that. So we went from 12, 10, 8, 6 up to 4 mil. So and it's still applicable. I'm sure if we have different different ranges of thickness, we'll probably need another sort of probe for it, because I think our probe is optimized for this kind of scope. But I'm sure if we require different pipes or different thicknesses or different parameters, we would definitely need to design a new probe.
Thank you. I don't see any other questions, so in that case, let's move on to our next speaker. Our next speaker is Paul, who is a second-year PhD student with Brunel University London, and he's talking about crack-tip constraint for steel in Arctic conditions.
Good morning, everyone. My name is Paul Sukpe, and I'll be presenting today on the crack-tip constraint in typical high-strength steels components in Arctic conditions. And this has now been narrowed down to just offshore pipelines. My project is sponsored by Lois Register Foundation and Brunel University, London. This is a brief outline of what I'll be presenting today, an introduction to the project, the testing method that will be employed, a bit on constraint, finite element analysis, conclusions, and future work. Constraint effect is a key issue in structural integrity assessment based on the two-parameter fracture mechanics to make a precise prediction of the load-bearing capacity of crack structural components. As such, defect assessment procedures such as the BS7910, the R6 and API 579 rely on the use of fracture toughness data usually measured from deeply notched specimen tested under bent loading to guarantee high levels of crack tip constraint around the crack tip, which drives the fracture process and give conservative predictions of failure. However, engineering such as oil and gas pipelines are predominantly loaded in tension and contain shallow cracks, which exhibit low levels of crack tip constraint, leading to an increase in the fracture toughness. And for the experimental plant, the importance of fracture behavior for low constraint crack structures has prompted the development of more refined defect assessment procedures capable of including the effects of constraint variation on fracture toughness. An XN of BS7910, for example, describe methods of including constraint effects in the analysis of metallic structures containing flaws so that the crack tip constraint in the test specimen closely matches that of the structural component that is to be tested, such as in pipelines. It is also known that experiments conducted usually assume that the actual stress intensity factors are in good agreement with theoretical solutions. But a lot of external and internal disturbances, such as small crack deflections, crack closure, and the test environment itself do distort the experiment, thereby affecting the values of the crack driving force. It is for this reason that the digital image correlation is being proposed to be adapted for this project to capture the actual loading and loading conditions in terms of displacement and then deformation fields as the test is being performed. Now, linear elastic and elastic plastic fracture mechanics are based on the concept that the stress fields around the crack tip can be characterized by a single parameter such as the stress intensity factor K, the J integral, or its counterpart, the crack tip opening displacement. When the plastic zone is small, such as in brittle materials, K is commonly used to characterize the stresses around the crack tip. But in data materials, as the plastic zone develops further around the crack tip, the stress intensity factor K is no longer valid. And then the J or the CTOD is then employed. For low constraint conditions, however, the single parameter alone, based on fracture mechanics, based on K or J alone, give conservative failure assessment using fracture toughness values that are taken normally from high constraint test specimens. Now, over the years, the two parameter fracture mechanics has been developed to account for the effects of constraint in providing more realistic analysis of low constraint crack geometries. The JT approach effectively quantifies crack tip constraint for low constraint conditions. This approach, however, has some limitations because the T stress is known to be an elastic parameter that becomes less meaningful as the plastic zone expands into the elastic plastic regime. It is for this reason that some researchers have studied the Q parameter to be able to quantify constraint in the elastic plastic regime. Now, these two parameters, the Q parameter and the T stress, have now been incorporated in BS 7910 and XN for constraint assessment using the so-called constraint-based failure assessment diagram methodology to describe the crafty stress fields for various geometries and loading conditions. In essence, an XN allows the quantification of constraint condition with the structure being assessed and the small scale specimen, such as the laboratory specimen used to assess it, using either the T stress or the Q parameter. The constraint level is quantified in terms of the load ratio, which can also be expressed in terms of the reference stress and the yield stress. And both of these parameters, both of these parameters are expressed in terms of the structural and the normalized structural constraint parameter beta, and where beta T and beta Q both depend on the geometry of the specimen or the structure, the flow size, material properties, in particular the strain hardening exponent, and the loading configurations. And it should be noted here that there are currently no lookup tables in BS 7910 and XN for the Q parameter, and it cannot also be easily standardized in the same way as the T stress because it depends on the stress strain curves of the material that is being tested, and also on the magnitude of the load. As part of this project, apart from the T stress and the Q parameter, third parameter TZ will also be computed in Abacus for thickness effect to account for the out of plane constraint. And as part of the finite element part of the project, in order to account for the global bending and tensile effects on the crafted stress fields, a series of finite element will be performed using the single edge notch 3-point bend tension specimen and the single edge notch tension specimen that are usually used to characterize pipeline steels within with thin wall thickness to identify the specimen to match the crafted constraint of the crack sections. Now, from linear elastic fracture mechanics, the problem of calculating stresses around the crack tip can be analyzed using linear constitutive relations, and the solution to the linear problem is usually singular at the crack tip. As the stresses and strains at the crack tip are singular, modeling singularity will require a considerable mesh refinement near the crack tip. It has been shown that 2D and 3D elements, the singularity at the crack tip is best described when the mid-side node is at the quarter point position. Now, so far for some FEA has been done using the 3-point bend specimen to illustrate the contour independence of the J integral and then the T stress.
Or you have 1 minute remaining.
Okay. I'll just go to the conclusions. In order to examine the effect of constraint, it is essential to have a measure of not only the normalized structure constraint, but also the dependence of the fracture, the material toughness on the constraint. And as, in conclusion, we hope to demonstrate the strong effects of specimen geometry and loading modes, both bending and tension, on the fracture behavior of ferritic structural steels in the data to brittle transition region to be able to capture the low temperature effects. Also, to account for constraint loss that contributes to the apparent increase in fracture toughness of shallow crack bend and tension specimens, and examine these constraint variations in terms of the JT as the 2-parameter or JQ methodology. And then some recommendations at the end of this project can be made to the available standards such as the BS 7910. Thank you very much.
Great, thank you very much, Paul. Just a reminder, if you have any questions for Paul, please do put them in chat. Yeah, Paul, there is a question from the chat. Says, what are the FY results indicating?
FY. FY, I don't understand. What's FY?
Just a question from sorry, FE, I apologize. FE results, I think it's a typing error.
Like I said, this were just to check the contour independence for the J integral, and then the T stress across the specimen thickness.
Okay. So if there are any other, yes, there's another question.
So Paul, thanks for your presentation. My question is that you are basing your PhD on the latest edition of BS 7910, yeah?
Yeah.
Yeah. So I don't know if you know the earlier versions of 7910 has got some tabulated solutions that have been subsequently taken out in the latest edition. Would you be considering that now, based on the outcome of your FEA, revisit those content that has been taken out and see how they compare?
Yes, I have considered revisiting the previous one, the 2013 one.
Yeah.
To compare with, because I know that some lookup tables have been taken out for some particular geometries. So I'll be comparing that to see the effect they will have on my models.
Okay, all right. And the reason why they've been taken out is just that the committee feel that is it would be easier for people with the computing power nowadays to determine these certain parameters from the FEA model than the lookup tables, and then feel that nobody has been using it. But I personally think that it would be nice to revisit those lookup tables, based on your research, and then maybe make a recommendation to the committee, especially for those users like me that are not very familiar with FEA, and what are the other alternatives that we can use. Yeah. Okay. Thank you.
Yeah. Thank you very much.
Thank you. We are due a break now. Lizzie, are you able to confirm what time we will restart, as we're running a little late?
Hi, James. Yeah,
Hi.
if we can come back at 11. So it's only a short 5-minute break, unfortunately, but yeah, if we can all come back at 11, that would be great.
Okay, we'll restart at 11. Have a very quick break. Great. Well, welcome back to this session. Our next speaker is Matthew, who's in his 3rd year of his PhD at the University of Bristol, talking about weld residual stress data.
Thanks, James. Yeah, just thanks everyone for coming today. So yeah, I've quite a lot of information to cover. So hopefully you can see that. Okay.
Yes, I can see it.
Is that fine? Okay. Well, all right. Let's crack on. So yeah. So my my talk today, I'm going to be going over some of parametric statistics using girth weld residual stress data. And what I'll be covering today is the motivation and industrial impact of this work, how residual stresses influence fracture, current advice regarding residual stress assumption in fracture assessment, and key literature, some experimental data, and presenting how the method of the parametric analysis, the results of that method, and then some conclusions and work that's going to stem on further from that. So, so to begin, I'd like to begin with the motivation of this work and its implications in industry. So it's quite well known that weld residual stresses influence fracture mechanisms and have the potential to cause structural failure. And it is important that this phenomenon is understood through the use of finite element modeling and experimental data, so that standards such as BSM 910 and R6 can give the best possible advice for treatment. So my PhD is focused on pipe girth welds, and this is still a very much widely used welding technique, both on and offshore. So as residual stress measurements have grown over the years, certain challenges have arisen. So one thing to point out is that residual stress measurements are quite difficult. And one of the reasons for this is because they require, in some cases, the breaking of a specimen, which is quite costly and time consuming. And other non-destructive methods can only be performed in certain locations and are limited to geometry size as well. So in general, there's not a lot of residual stress data out there. And because of this, it's quite difficult to give accurate recommendations. So what I'll be presenting today is the standards do give some advice on residual stresses, and these are certain parameters. And I'll be looking towards other parameters which aren't currently considered and seeing if they have potential to influence weld residual stress, and what this could mean for future editions for BSM 910 and residual stresses in general. So, so what are residual stresses and why are they important? So in general, they can accelerate crack growth, and this is dependent on whether your crack is in a tensile region or a compressive region. And these can change depending on the location of the crack, depending on the weld processes, and most importantly, these are not always known. So you might have a weld, but you don't have a measurement for that weld, so you have to assume them in most cases. So this is why BSM 910 recommends profiles, and this is the level 2 profile of residual stress, and this is dependent on the heat input and whether your weld is either austenitic or ferritic. And these include, importantly, the weld centerline and also heat affected zone regions of the weld themselves. So these cover quite a large range of different pipes. And because it's only dependent on 2 properties, you can give a very general estimate, and these are upper bound estimates based on that. But what I'll be talking about today is what other parameters that aren't considered might also have an influence on residual stress and what that could potentially mean. So as I mentioned, these are naturally conservative, so we want to try and be more realistic with our residual stress assumption. So some literature surrounding this topic. This is the work from Pishu Dong, and there's been quite a lot of interest in this parameter called R/T, which is the outer pipe radius divided by its wall thickness. And as you can see in the bottom right, these can vary quite a lot. And so a low R/T will have a very small radius and a very thick pipe, and a much higher R/T will have a much thinner pipe structure with a much larger pipe radius. And the thinking behind it is that a much smaller pipe will have a lot more natural constraint, and that will affect how residual stresses develop in the weld and in the pipe itself. And so here are some of the results from this work in literature, which shows that there are indeed some influence of residual stress, or some influence of R/T on residual stress, particularly towards the pipe inner surface. These are all done through FEA, so no experimental validation has been done doing this. And one more important thing is to point out is that as you approach higher R over T values, your pipe radius or your pipe curvature becomes more flat, becomes more like a flat plate. So you might want to use a different treatment than if you were to use a very much lower R over T value. So that's what the literature says. And so we are trying to kind of back that up with experimental data as well. So here is a database which I've gathered from literature, and just to point out on the y-axis the residual stresses have been normalized to the parent material yield strength, and the normalized distance has been normalized by the material wall thickness. So first off, these are the weld centerline data and the heat affected zone data, and I plotted them together just to see or just to show that they're indeed, they look quite similar. They have very similar magnitudes, similar peaks, and one of the things that I'm looking to investigate here is whether we can actually treat them the same as suggested in standards. So overall, there's quite a lot of data here, so we can do some statistical analysis, and importantly, this is a large range of different pipes, so different parameters, different geometries, and we want to kind of compare what differences of the parameters might have on the residual stress. So we're doing this through statistical methods. So we're testing how the data is distributed. And I've done some previous work which suggested that residual stresses are distributed using or can be represented using a normal distribution. And these have been done using KS tests or Kolmogorov-Smirnov tests. And I've done other statistical tests, but I haven't presented them here. And with this assumption, if your data is normally distributed, you can do further two-sample t-tests, which I'll go into more detail further on. So just a little bit of background. So as I mentioned, different welding techniques, different measurement techniques, and these will typically have different resolutions. So you will have a high resolution data set next to a very low resolution data set. So you might have some over or under fitting because of this. And so one way around this is I plotted a polynomial of each individual through thickness measurement. And using that polynomial equation, you can actually use this to say at each individual depth, at any given individual depth, this is the residual stresses which occur. So there are some inaccuracies involved in this method, but as you can see, they're not particularly high as long as you're plotting your polynomial within the measurement data itself and not trying to predict anything outside of that. So here I've shown that the weld centerline data and the heat effector zone data are both normally distributed, quite a strong correlation there, and because of that we can go on to further statistical tests using two-sample t-tests. So this is just an example of what that looks like. This is two normal distributions of each of the data sets, and the correlation is how well they overlap with each other. The more overlap means they're better correlated and they can be considered from the same data pool. So the data or the results show that there's very good correlation between the weld centerline and HAZ measurements, and importantly, this is backing up what the standards already say about weld residual stress treatment, which is that they can be treated the same. And I just want to quickly add in that the HAZ measurements are measured pretty much all at the same location at the end of the last capping pass.
You have 1 minute left, Matthew.
Sure, thanks. And so there's quite good amount of data at that one particular region. So we can say that they are the same, we can treat them as the same. So so using this analysis, we're investigating RPT here. And so what I've done is I've compartmentalized each of the data sets from the database into low, medium, high R/T values, and basically compared them against each other using the 2-sample t-test and showing if these data sets are correlated. So as you can see, there's quite a big gap between the low, medium, and the high. What the data shows us is that there's good correlation between the low and medium data groups, which is quite obvious because they're quite similar. But then as you compare them with the higher data groups, they're much, much lower. So what this does show is that there is dependence on R/T, especially between lower R/T and higher R/T values. And just to kind of conclude what this work has done and what it's going to do. So firstly, we've found out that the treatment regarding sense line Hans regions are in fact quite good. The data agrees with that. And we have shown that the lower R/T values may have a different effect on residual stress than higher R/T values. And in regards to treatment in current standards, should we change the treatment in current standards? Probably not based on this work, because of the general agreement in the data was quite good. There wasn't significant difference. So there's not a immediate action doesn't have to be taken regarding these different pipe geometries. So future work, other work that we're going to do stemming off from this is investigate other parameters, welding processes, things like that, and actually specify what the differences are, not just saying that there is a difference, but specifying what those differences are, and then hoping to conclude what different parameters might, how they might influence residual stress and in fracture assessment. So thanks everyone for your attention. Here's my sponsors, NSIRC, UKRI and Bristol. So thanks for your attention. Is there any questions?
Right, thank you very much. Yeah, there has been a question asked by Luke, which says there tends to be a trend around 30 to 40% of the normalized distance from the inner surface of compressive residual stresses. Does this cause a specific type of failure under operational loading?
I guess it would depend on if there was a flaw in that location. If there's compressive stresses, then typically your the probability of failure would be lower, because it's kind of closing the crack opening displacement. So if you can confirm there's compressive stresses, then you probably don't need to worry about it as much as tensile stresses.
Okay, thank you.
Can I ask a quick question? Matthew, hi Matthew.
Hi Rob.
You mentioned the KS normality test that you
Yes.
did, and you said you had a look at some others as well, but you sort of didn't present them there. Was there a reason that you chose that one to demonstrate normality rather than any of the others, or did it just look the most pleasing?
Well, yeah, the statistical testing is quite a difficult. You have to be quite precise, because each test has its own limitations, and especially the KS tests they're more sensitive towards the mean values of your data. So if there's a variation in the mean, it's going to pick that up more easily than if it was towards the outer tails of the data set. So that's when you want to use other tests, such as Anderson-Darling test is another one. And there's also other adaptations that you can use. But in general, KS tests are the most popular, but aren't necessarily the best statistical tests, especially dependent on data size and things like that. So you want to kind of cover all bases before you're saying, yeah, this is what we found, because you might not, that might not be true at the end of the day. So.
Okay, great, thanks.
Thanks, Rob.
Great, thank you very much, Matthew. I think we move on now to our fourth speaker, who is Oliver, in the third year of his PhD with University of Bristol, talking about notch fracture toughness.
I'm not sure we've got Oliver in the room just yet.
Okay, let's hope.
We did have, but he might have dropped out. Oh,
He's just put I am here in the chat.
Here we go.
Yes, we can see your screen.
Yeah, there we go. Hopefully everyone can see me and hear me now. Sorry, I don't know why I didn't appear to start with. Yeah, hi, my name is Oliver Logan. I'm a PhD student with TWI and NSIRC and the University of Bristol. And today we'll be talking to you about a constraint analysis approach and specifically an application of it towards notched cases. As we know, real life defects aren't often the idealized sharp cracks that we often assume them to be. And in fact, we can see very blunt or very spherical defects often present in from manufacturing or from corrosion or welding. And my project and my PhD has been looking to bridge the gap between this fatigue pre-cracked idealized assessment and then a larger locally thinned area plastic collapse assessment, seeking to fill in this green area on the graph on the right and how we may make use of more knowledge and complete the picture. Previous work has shown that there is an increased effective J or effective fracture toughness as notch tip radius increases, in some cases quite dramatically so, from a fatigue pre-crack and moving to a blunt parallel-sided notch. This has been shown by both Horn and Sherry and Hannesel in the cleavage regime and the ductile regime. However, my work itself has been more focused on the cleavage regime. And from the constraint side of things, there is a work that shows that there is a constraint approach that allows us to modify for fatigue pre-cracks or sharp cracks and make allowances for different loading conditions or different constraint at the notch tip. This is measured by a value of Q, which is a measure of change in the stress field of the loading conditions to a high constraint stress condition. Although we know that these are different mechanisms, moving from a high constraint fatigue crack to a lower constraint fatigue crack compared to moving from a fatigue pre-crack to a notch, we hope to use a similar method to assess the both constraint losses combined. And we hope to use this definition or a modified Q row to assess both effects together. My work started with a large range of experimental testing, mainly carried out on single edge notch bend specimens with several fatigue pre-crack specimens to compare the results to as a baseline. Notch specimens were machined using EDM to a curved notch tip radii, 0.2 mil, 0.5 mil, and 1 millimeter notch tip radius. The specimens were all machined from a S355 J2 plus N plate of steel, and the material properties are as shown on screen. The results of these tests allowed us to calculate an effective J for the notch specimens, and as expected, we can see a very large scatter in the results, which is kind of why we did as many repeats as we did, and these could then be translated into a effective notch fracture toughness using the value of E and Poisson ratio shown on screen, which allowed us to compare these results to other results from literature. This is a very similar cleavage test program that's carried out on a very similar material, an S355 J2. Although the specimens in this case were a CT specimen, a compact tension specimen, our belief is that both were very high constraint at the notch tip and allow us to compare the results to compare the levels of scatter at different notch tip radii and see where our results or their results might be more scattered than you might expect. We see good trend at the higher levels of notch tip radii, and maybe we have slightly more scatter, the 0.2 and the 0.5 mil, than they have here. This led us into some numerical modeling. As discussed earlier, Q is assessing the level of the stress field between our stress field of interest with a high constraint stress field, and Q is then assessed at a normalized distance ahead of the notch tip of R sigma 0 over J equal to 2. Initial modeling was carried out on single edge notch bend models. A quarter model was modeled with elastic plastic material properties. However, we were seeing edge effects impacting the stress fields of the higher levels of J. Because of the desire to decouple the notch tip effects from the boundary effects, we moved to modified boundary layer modeling, which is a large semicircular model to remove the boundary effects. By applying specific values of J or KJ and T stresses, we were able to simulate the SEMB scenarios in both 2D and 3D. Our 3D models also showed the impact of these very high levels of J. At low levels of J and towards mid levels, we were seeing a very good correlation between our 3D models and our 2D plane strain conditions. However, at very high levels of J, up to J of 1,000, which is about the level of effective J failure for our 1 mil notch tip radius, we're seeing large discrepancies between the stress fields of the 3D models and the 2D plane strain model. Because of the desire to only focus on the constraint effects of the notch tip radius and not the thickness effects at this time, we decided to move just to a 2D plane strain model. And the stress fields here show how the simple shift from a cracked model to a 0.5 notch model moves the position of peak stress down and to the right, smoothing the curve and meaning that the stress field is much less severe. However, we had the downsides that because of this shift down and to the right, our assessment of Q at R sigma 0 over J equal to 2 may not always be valid and may not always give a true definition, as we are assessing it. We're not always assessing it in the J dominant zone, and maybe even assessing it before the position of peak stress at these low values of J for the notched models. So to bring back to the traditional Q assessment, we've decided to propose an alternative Q row assessment. This shifts the normalized distance to R prime instead of R, which is the distance ahead of the crack tip minus the position of peak stress. By comparing the stress field of the notch model and the stress field of the cracked model at this new R prime sigma 0 over J equal to N, where we can vary N, but for now we'll keep it equal to 2, we hope to give a different but also valid Q row assessment. The nice benefit of this is that by shifting the data by the position of peak stress, the cracked models remain largely in the same position, which means that cracked constraint assessments using this method will remain basically the same. But shifting the notch models to their position by their position of peak stress can dramatically shift them in some cases, but allows us to investigate the stress fields ahead of the crack tip. It's worth pointing out that previous work has shown that crack initiation in notch models often correlates with the position of peak stress, and that's why we felt validated in moving them by this amount. A Q assessment can then be carried out here in much the same way as before. This gives us a measure of Q, which we can plot versus J or plot versus the fracture toughness of the effective fracture toughness, and we can begin to determine a relationship between notch tip radius, so the level of constraint change, and J or our notch tip radius of our specimens. So the next steps for this work are for this Q method, are to define the relationship between loss of constraint and the notched effective fracture toughness over the fracture toughness of the material with a crack, and investigate how this Q row varies with distance ahead of the peak stress, and also to get into the lab to confirm whether our results follow this, that the crack initiation site is near to the position of peak stress. An alternative approach, which are just in the beginning stages of developing and investigating, another constraint approach though, is to look at an equivalent crack approach using beta T or beta T row. This is using a measure of T stress to compare our notch specimens to our cracked specimens, and then using relationships as defined for cracked specimens to see if we can find an equivalent crack by varying the depth A over W. I thank you very much for listening, and I do welcome any questions.
Thank you very much. So please, if you do have any questions for Oliver, put them in the chat. I think immediately I have one, which is you have talking very much about specific notch radii. So you're talking about 2 millimeter and so on. How dependent are your results on the notch radius as opposed to the relationship between the notch radius and the specimen geometry, so thicknesses or widths or other things like that?
Sure. So for now, I suppose we've only looked at various notch tip radii. The specifics were chosen to line up with a sister PhD looking at sizing notch tip radii. So that's kind of why specific sizes were selected. It is true that there is some work that shows that specimen geometry that's defined for fatigue pre-cracked specimens may not give the suitable, or is not suitable for notch specimens. And future work is planned on looking at different specimen thicknesses, as was kind of highlighted with the MBL work, looking at increased thicknesses, to look at different thicknesses in an SEMB test with the different notch tip radii. But yeah, I know I understand there definitely is an impact of specimen thickness though, as notch tip radius increases. The whole thing is a bit of a complicated intertangled mess, and we're hoping to try and separate out the parts so we can figure out kind of exactly which bits impact what.
So you're mainly focusing on a specific specimen geometry and therefore notch tips.
Yeah, for now we're focused solely on an SEMB specimen of a specific thickness, but we would like to expand our testing program to still in an SEMB specimen with a high constraint, but potentially different thicknesses to cover those questions. Yes.
Thank you. Are there any other questions for Oliver?
Yeah, one from me. It's a bit of an unfair one from me, Oliver. So this is really good stuff, and I'm just wondering, like, how we would be able to convince ourselves in an assessment that we did actually have a notched configuration rather than a situation where there were a sort of sharp feature emanating from a notch that would sort of necessitate we used regular assessment with assuming sharp cracked it. Have you got any thoughts on that? I know it's sort of a bit outside of your scope.
Yeah, no,
have you got any thoughts on how we might sort of convince ourselves that we could actually use these types of procedures in the future?
Yeah, sure. So I suppose this is, you're going to have scenarios where, although my PhD isn't actually evolved in the sizing or identification of non-sharp defects, part of my research group, there's a postdoc working on that very question. So that's kind of the PhD and the postdoc kind of working in tandem. He's looking at sizing of defects and kind of identifying. In terms of whether you can convince yourself that it's definitely a non-sharp defect, you get very spherical defects in things like additive manufacturing, where you might get cases where the component has not been under any load yet, and you might be more confident in that case to assume that it is a non-sharp defect. And other methods that cause damage to components, I suppose, like corrosion or pitting, generally causes non-sharp defects rather than like fatigue cracks. And in those cases, you might be more confident using this approach.
Yeah, that's great. Thank you.
Thanks.
Thank you very much. So our final presentation of this session is a core research program showcase presentation by Muhammad Ali on refill friction stir spot welding for aluminium alloys.
Hello, James.
Hello, we can hear you.
I don't think you have picked the correct title for my presentation.
I apologize for that. I'll let you give the correct title.
So I need to share my screen first, if I'm allowed to. Yeah, I don't know much about welding, James. Sorry.
Oh, okay. I've been given completely the wrong title, so I apologize for that, and I'll let
It's all
you
right.
cover
No
your
problem. Thank you very much for inviting me for this presentation. My name is Muhammad Ali, and I think many of you know me that I have been working in fracture integrity section for several years within TWI. I joined TWI about 15 years ago, and I started my career as a project leader in fracture integrity management section, and then I moved on to a team manager and a section manager. But I have worked a lot on different single client projects as well as co-research projects. And the part of the work I'm presenting in today's presentation is related to one of the co-research projects which we started a few years ago. Although we could not complete that research, but I think it's worth presenting one part of that project, which was related to evaluating fracture resistance of a material under sour service conditions. Now, the title is pretty generic, but when I move on to how we did this work and what were the main objectives, then it will take you to a more focused scenario. Sour environment. We are all familiar with this, that sour environment is an environment which can compromise the performance of an engineering structure, any engineering structure which experiences such environment. The most prominent examples are those structures in oil and gas industry, such as pipelines, pressure vessels, and other infrastructures. Similarly, if we go to renewable industry, in particular offshore wind turbines, which are used to generate energy through wind. If you look at the foundations of those wind turbines, which are basically very large monopile structures embedded in the seabed. However, they are usually protected using a technique called cathodic protection, which can liberate hydrogen, and that hydrogen can ingress into the material to embrittle that material. Now, hydrogen embrittlement and effect of sour environment, they are very commonly used. However, hydrogen embrittlement itself is a mechanism which occurs under sour service conditions. However, hydrogen embrittlement can also occur for those structures or for those containers which are used to store hydrogen, if the situation is such that atomic hydrogen can ingress into the material and embrittle the component. There are several historical examples of failure under sour service condition or under hydrogen embrittling condition. The most prominent one was the failure of an amine absorber tower in Union Oil Refinery. That was the history, one of the most important examples in the history where the failure occurred as a result of hydrogen embrittlement. There are several other studies on stress corrosion cracking or cracking due to hydrogen embrittlement. And these are a few examples of the type of cracks which can exist in the structure. And if these cracks are exposed to any severe or sour environment, then the stability or resistance of these cracks to external loading can significantly be compromised. We are familiar with some of the terminologies. I'm just trying to recap some of them. For example, stress corrosion cracking is a very generic term which is used to describe a failure under a combined effect of stress and corrosion. However, a more specific term is sulfide stress corrosion cracking, which is a type of cracking occur under sour service conditions. And these conditions could be dominant under various situations, for example, crude oil, decaying organic matter, seabed, etc. However, we call an environment to be sour if the hydrogen sulfide content in that environment is above a certain threshold level, which are basically defined in various ways, and the susceptibility of a material to H2S environment, or the susceptibility of a material to failure under H2S environment, is also dependent on the properties of that material as well. Moving forward, hydrogen embrittlement. As I have said, that this is one of the most dominant phenomena of failure which occur under sour surface conditions. What hydrogen actually does, that interstitial hydrogen atoms can reduce the cohesive strength of a structure, and hence they can also reduce the fracture resistance of the material. The most prominent effects of hydrogen embrittlement are loss of ductility, loss of strength, increase in hardness, and loss of toughness. In a more sophisticated way, when we carry out engineering critical assessment of structures, we come across three elements which are necessary to evaluate the safety of the structure under static stresses. Apart from applied stress and flow size and geometry of the component, the third important parameter is materials properties, which is composed of yield strength and fracture resistance. And both of them can be compromised in the presence of diffusible hydrogen. We are interested here in fracture resistance because fracture resistance is more prone to drop if interstitial hydrogen atoms are present under applied stress, and they can preferably concentrate at the crack tip where high tensile stress triaxiality exists, and therefore high potential energy. Those who have a background in fracture mechanics are familiar with this diagram. This is called failure assessment diagram. But for those who do not have much interest in fracture mechanics, this is the diagram between two parameters. The first parameter is called fracture parameter. The second parameter is called the loading parameter. The fracture parameter is the ratio of applied stress intensity factor to the fracture toughness of the material, while the loading parameter is the ratio of the reference stress and the yield stress. This reference stress, various reference stress solutions are available in different standards and different textbooks. This parameter is dependent on the applied loading as well as the geometry of the component. The diagram is a curve between these two parameters. This curve is called as a curve which defines the acceptance or non-acceptance of a flaw. For example, when we assess a crack in a component under applied loading, our assessment result can come up to a point which can either lie below this line or above this line. If this is below this line, it is called safe, and if it is above this line, it is called unsafe. So this is the fundamental principle when we assess fracture safety of a component. And my main work here is based on an experimental technique which is used to determine fracture toughness parameter, which is used as one of the most important parameters to assess the safety under using this procedure. Main objectives. There were two objectives. The first objective was to evaluate fracture toughness and define the most acceptable technique to determine fracture resistance of a material using techniques available in different standards. And the second objective was to use numerical modeling to develop a better understanding of how hydrogen diffusion can affect fracture toughness and how experimental results can be demonstrated through a numerical analysis technique. The numerical analysis was carried out by my colleague, Tyler London. He is working as the section manager of a section called numerical modeling within TWI. A brief summary of the contents. We started this work by reviewing existing guidance on determining fracture toughness of material under sour surface condition. Then I will briefly explain the test program, some of the test results and numerical modeling results, implications on engineering critical assessment, summary, and further recommendations. We started our work by reviewing different standards, and as you will appreciate that determining fracture resistance under sour surface condition is one of the active research area. There are several challenges which we practically experience when we try to execute a test program. There are several standards starting from those who only define methods to determine toughness, which can subsequently be used for qualitative purposes. The most prominent one are some of the ASTM standards and ASTM 0177. However, there are some standards which provide more detailed guidance on how to determine fracture toughness and how to define the fracture toughness parameter, which can be used in any integrity assessment procedure. And I think the most prominent one was DNVGL, recommended practice at 108. We try to use some of the guidance given in this standard combined with the guidance given in other BS standards on fracture toughness testing here. Here is the brief description of the test program. We used API 5L X65 steel, which is most commonly used in oil and gas industry. We use single edge notch bend specimens. We used a rising load testing methodology. The testing method was similar to those given in well-known fracture toughness testing standards developed for testing in air. We presented our results as fracture toughness J integral versus crack length measured during the test. The test solution we used was moderately sour with a pH of 4 and H2S concentration of 10% ballast CO2. We agreed on this environment after discussing with some of the oil and gas companies. Some of the key results. Now we produced various results. We did several very slow loading rate tests under the defined sour environment. So as a first task, we attempted to determine an optimistic loading rate, which can be used to produce results which are closer to the lower bound fracture toughness we usually use in assessments. The tests were carried out at loading rates, which we often measure as K rate, or the rate of change of applied stress intensity factor in megapascal Newton per meter root meter square. The loading rates we used were about 5,000 times to 50,000 times slower than the loading rates we normally use when we test in air. So that can also tell us how time consuming a fracture toughness test program in environment could be. These are the results in the form of tests conducted at an optimum loading rate of 0.305 MPa root meter square. And we compared these results from some of the previous work where we did the same test under the same loading rates, and these results are pretty comparable. Now, moving forward to some of the integrity assessment procedures we often utilize to determine safety of a structure under static load. BS 7910 and DNVGL RP 108 are the most frequently used standards. However, there is no clear guidance on once you carry out a fracture toughness test program in a sour environment, how you will determine fracture toughness, or how confident you are to pick a fracture toughness number and utilize that number in any of your safety assessments. So this was the biggest challenge. If you look at guidance given in BS 7910, the latest edition, it says that all assessments should be carried out using a fracture toughness number below which no time-dependent crack extension can occur. Similarly, DNVGL RP 108 suggests that rising load tests should be combined with some static load tests to ensure that whatever fracture toughness parameter you define to be used in safety assessment should show no time-dependent crack extension under the specified loading conditions. Here is some a diagrammatic demonstration of two types of static load tests. The first test is when you subject a specimen to a defined force level, leave it there for some time and see if there is any crack extension. If no, then step it up until you see a crack extension, and then use the data from initiation to the end and define a threshold level and also a threshold stress intensity factor at which no crack extension occurs under sustained load. There is a simplistic way to do this test is a constant load test. Now DNV GL RP 108 provide these two guidance on these two tests. However, they leave it to the expert to define an appropriate fracture toughness parameter to be used in any specific assessment. We have tried to combine both of these testing methods, the rising load testing method and the static load testing method. So what we did, we combined the R curve results determined through the rising load test and also two tests conducted at a constant displacement. The method was that we subjected the specimen to a very slow rising load until to a point where the specimen was left in displacement control for a long period, which was 45 days in this case. During that period, the aim was to see whether the equipment shows any crack extension during this period. In one test, we did not see any significant crack extension. However, the other test failed and we had to repeat that test. Unfortunately, this part was not completely successful. However, we reached to a point where we can perceive that there won't be any further crack growth at the defined load level, and any R curve developed up to that point can be used in any assessment. I would say that this result does not mean that the assessment should be done using this particular number, but this just provides us a guidance how to define toughness and what are the chances of carrying out a successful test, especially the test under displacement control. By combining all this data, we defined an artificial lower bound R curve, which we attempted to use in the subsequent ECA. Parallel to that, this work was carried out by my colleague Tyler London. The modeling can help to provide an understanding of the interplay between hydrogen diffusion and hydrogen diffusion concentration and the elastic plastic stress fields. A validated model can enable for quantities to be calculated that could not otherwise be readily measured through a test. If you see that the modeling results were very close to the test results, however, the modeling can help to define various parameters which are very difficult to determine or to show during a test program. Similarly, some other modeling results showed that how elastic plastic stress field and crack size can change the level of hydrogen concentration ahead of the crack tip. We tried to plug the results from the test into ECA. This ECA model was just to show how using a conventional very low single point fracture toughness parameter in terms of K1 SCC make a huge difference if we use a partial R curve derived from this test program. So in terms of flaw tolerance levels, you can see that if we use single point fracture toughness numbers in our assessment, the flaw tolerance level yielded by the procedure are even lower than the detectability limit of any inspection technique often used for inspection purposes. In other words, these results are literally meaningless. However, if we use a partial R curve derived from the current methodology, then the flaw tolerance level can be improved. It is very important that the test methodology, whatever the methodology is used, there should be high level of confidence in the number in the form of single point fracture toughness value or a partial R curve, which we use in any safety assessments. Based on all the learnings, previous experiences, and the current work, we have defined a guidance of how to implement, how to carry out an ECA in the presence of the available information. Now, I'm not going through this diagram because it's quite complicated, but it can give you a defined path to be adopted if you have certain type of data available or not available. The ultimate aim is to minimize the unnecessary conservatism which we often build in an assessment when we carry it out for a structure exposed to normal or air environment rather than sour environments. Some of the conclusions: there is some guidance available in existing standards. However, a lot of work is required to be done to agree on a universally acceptable method. In terms of convenience and practicality, it was found that a K rate, a defined K rate within this range, can provide a fracture toughness reasonably close to the expected lower bound fracture toughness. Now, using the guidance given by DNV to determine fracture toughness or to define an appropriate fracture toughness parameter through a combination of R-curve testing and static load testing is the most challenging part of this test program, because each test almost takes a month to complete, and if you are lucky, you can complete 3 tests successfully without any interruption. But that test program is, looking at the minimum number of required tests which are necessary to be utilized when you follow any well-established integrity assessment procedure, they require at least 6 months to be complete. Using finite element modeling technique, a multi-physics model of hydrogen diffusion and ductile crack growth has been developed through this test program. The results demonstrate that the hydrogen concentration ahead of the crack tip can reach approximately twice the initial hydrogen concentration in the specimen. Similarly, ECA based upon single point fracture toughness values as well as lower bound partial R curves have shown that the latter can yield higher flow tolerance level than the former, the extent of which depends on the applied stress and the maximum crack extension in the R test. We came up with a lot of recommendations. I just tried to summarize some of them. Of course, the fundamental recommendation, the basic recommendation is that any sour fracture toughness test program should be well synchronized with the relevant integrity assessment standard. And allowance for loading rate sensitivity tests should be given in all fracture toughness test program depending on the severity of the environment. It is not necessary to stick to a very, very slow loading rate given in some of the standards. The loading rate could be faster depending on the severity of the environment and other service conditions we experience. Determination of partial R curve should be supported by at least a set of 2 tests at the point of stability to ensure that there is no static crack growth under sustained displacement hold or for a specified length of time. And finally, it is important to note that the test solution reflects the service environment as accurately as possible. And I think this has been stipulated in many well-established guidances, for example, BS 791. I'm sure you are using question and answer option already, but that's where my presentation ends. Thank you very much for your patience. This is a very complicated topic and I might not have covered everything, but please feel free to contact me directly or use this form if you have any questions. Thanks, James.
Great, thank you very much, Mohammed. Just checking. So if there are any questions for Mohammed, please do put them in the Q&A session. You've mentioned the challenges of doing these experiments. How easy would it be to use these sort of numerical simulations to gain a lot of the information from experiments, or you need to have these experiments done anyway to support the numerical simulations?
I think that's a very good question, and that was the reason we attempted to utilize numerical modeling to see. I mean, for the testing we have done so far, it very well, the numerical modeling results are very well in compliant with what we achieved through tests. But as I said, the main input you get is from a test program. So once we reach to a situation where we have generated a lot of sour fracture toughness data for various environments, for various materials, then we might be in a position to demonstrate more that through numerical modeling and use numerical modeling instead of carrying out a very, very large and expensive and time-consuming test program. But we are not at this stage yet.
Okay, thank you. And a question from the audience. Did the work lead to the publication of an industrial members report?
Yes, it did.
Is there a title or something maybe you could give for the people who have access to them?
Yes, the title is Evaluating Fracture Resistance of Carbon Manganese Steel under Sour Service Conditions.
Great, thank you. Are there any other questions? Well, in which case, I would like to thank Mohammed and the other four speakers, Oliver, Matthew, Paul, and Faris, for a very interesting session this morning. I believe we now have a lunch break, and the hosts could confirm the starting time of the afternoon session.
Thank you very much, James, and thanks to all our speakers. So we'll break now for lunch, and then we'll resume at 1 o'clock.
Thank you very much.
Okay.
Good afternoon and welcome to the session on joining technologies. This session is sponsored by TWI Certification Limited and College University. My name is Nenad Đorđević. I'm chair of this session, and we'll have 4 speakers today, starting from Dimitrios, who is a third-year PhD student at Brunel University, London. Please send us questions in the Q&A box, and we'll answer those at the end of the presentation. That's all for me. Dimitrios, over to you.
Thank you very much, Nena. Okay. Can you see my screen?
Yeah, we can see this.
Okay, just a moment. Hi, everyone. I'm Dimitrios Gaitanelis. I'm a PhD student at the Advanced Composites and Adhesive section, Brunel University, London. The title of my presentation today is Thermal Degradation of Thermoplastic Composites in Laser Processing, and the whole investigation takes place for composite metal joining. So the motivation behind the study is dissimilar joining of composites with metals. As you all know, in the aerospace industry, nowadays the predominant methods are mechanical fastening and adhesive bonding. Those methods work quite okay, but they have several disadvantages. For example, chemical fastening increases the weight of the mass of the plane. Adhesive bonding requires a very detailed surface pretreatment in order to make a very good joint. So the whole process is a bit cost ineffective. So you can understand that the industry and academia are very interested into looking new joining methods, and they're trying to develop several of them. And usually these methods involve high temperature processes. For example, the ones that you can see in figure 2, such as laser welding, friction stir welding, electron beam welding. The main issue, though, in this kind of processes is that the metal requires temperatures that are very high for the polymer matrix. So by increasing the temperature in order to make the joint, you can actually damage the polymer matrix of the composite. And by inducing this thermal damage on the polymer matrix, you affect the performance of the joint. Thermally degrading the polymer matrix of the composite can cause porosities, delamination, can cause several issues, degrade the mechanical properties of the composite, and reduce the strength of the joint. But what happens if we apply very high temperatures for a very short amount of time? That's what we're trying to investigate in the PhD. The idea is to identify the area that you can reach very high temperatures for a few milliseconds, for example, for a very short amount of time, that the temperatures are enough, are okay to create a joint without damaging the composite material. So high temperature short duration processing is examined. The material is carbon fiber reinforced polyethylene ketone, carbon fiber PEEK. It's a thermoplastic composite. And finally, we also investigate what happens to the interface properties between the fiber and the matrix when excessive heating is applied. So what is the addition between the two constituents of the composite and how this is affected before and after the heating treatment? In order to answer on these objectives, we use several numerical and experimental tools. And in summary, you can see the four aspects that are examined in this slide. First of all, a coupled thermal chemical numerical model is developed. This takes place in Abacus software, and Abacus routines are used. We use this model in order to identify the laser processing conditions that reach high temperatures without degrading the material. And the important element of the model is that the peak kinetics, the kinetics of the polymer matrix, are implemented in the model. Then an assessment methodology is developed in order to identify whether the material has been thermally degraded or not after the heating treatment. This involves a multi-technique analysis with several experimental methods, such as FTIR, DSC, and nanoindentation. In detail, FTIR is used to be able to detect whether degradation has happened, whether thermal damage has been induced on the material after the laser heating. DSC will be used to assess the crystallinity of the material after the heating treatment. Crystallinity can give us a very good idea on the mechanical properties of the material after laser heating has been applied. And finally, nanoindentation will be used in order to assess the mechanical properties of the material after the laser heating. Also, as I said before, fiber matrix interface is examined, and I perform single fiber pull-out tests in order to assess the interface properties before and after the heating treatment. Single fiber pull-out test is a very known test in academia. It's not a standardized test, but we have managed to make some good results in the TWI labs. And finally, acquiring all this knowledge from these three initial aspects, I'm planning to examine the effect of thermal degradation on a metal composite joint. So we will manufacture a composite metal joint, and then we will examine how much, if we thermally degrade the joint in the composite, how much will this affect the performance of the joint, and what is the acceptable thermal limits of the material. So just to make things a bit more clear for you, I would like to present you here the results of the thermogrammetric analysis. I don't want to get in a lot of technical detail. I just want to show you the area of interest that we examine in this PhD. We're interested into looking the area where we reach very high temperatures, but we do not degrade the material. So in high temperature short duration processing, where we want to reach as high temperatures as possible for a very short amount of time, we want to make sure that we are in the area where degradation has not started to happen, like as you can see in the black box here. And in order to do so, we proceed to several methods. As I said before, a coupled thermal chemical numerical model is developed. The interesting element is that it has implemented the kinetics of the matrix. The material properties are modeled to be dependent on the degree of degradation. So instead of saying that after 600 degrees Celsius, you have these properties, we say that the material properties fluctuate considering the virgin and the blend material. So they fluctuate between these two stages. This is, provides a bit more accurate representation of the whole phenomena because it takes into account the fact that if you heat a composite at 600 degrees for 1 hour, it's going to get fully burnt. But if you heat it for a few milliseconds, it might not have an effect. So we use this model, we have developed this model, and we examine Gaussian and top hat laser heating. And the main result of the model is that we have identified the process window where we can reach high temperatures without degrading the material, which you can see here. You can see the results in the green area is the results where for a specific heating duration between half a millisecond to 18 milliseconds, which is the power density that degrades the material just 1%. And the green area is the one that we can achieve very high temperatures without damaging thermally our carbon fiber peak. This investigation has taken place for both the Gaussian laser and the top hat laser. However, a problem that we have in laser heating in general, when we're talking about very short amount of time, like a few milliseconds, 3 milliseconds, for example, to make things clear, the difficult thing is to measure the temperature. So it's not very easy experimentally to acquire a value for the temperature. And you can't really say that, as I said before, 800 degrees for 3 milliseconds, is that bad for the material? Does it destroy it or not? So we proceed to developing a thermal degradation assessment methodology, which takes place initially with Fourier transform infrared spectroscopy, FTIR analysis. And we examine thermal degraded peak and carbon fiber peak, samples that have lost their mass from 0.5% up to 15%. Those samples have been heated, have reached this mass loss percentage by being heated with several heating rates from 5 degrees Celsius per minute up to 100 degrees Celsius per minute. And we have examined these samples with FTIR, and the spectral changes that are detected can be seen, for instance, in figure 9. This new fluorescent peak that is detected, it is shown that as degradation progresses, its intensity progresses as well. So besides being a very clear indication that the material has been thermally damaged, it can also be used as a tool for quantifying the amount of degradation that has happened to the material after heating treatment. Okay, can you see my slide? Okay. So here, just to make things a bit more clear, sorry. We have all the results for the intensity of the fluorescent peak, the one that is correlated to degradation for several heating rates from 5 degrees Celsius per minute up to 100 degrees Celsius per minute. And you can see that for each sample, for 0.5% mass loss, 1.2%, 4%, and 15% mass loss, the intensity is quite similar of the fluorescent peak. So this shows that the intensity of this particular peak can be used as a tool for detecting the degradation and as a tool to quantify what is the amount of degradation that has been reached. By knowing that and by doing the following experimental methods, DSCN and indentation, we can identify after laser heating that the material has been degraded by 1%, for example, and what does this 1% mean for the mechanical properties of the material and the crystallinity of the material, and for the performance of the joint eventually. The other technique that we are using, the other science that we examine in this PhD is the fiber matrix interface, as I already said, in order to examine the interface properties of the material of the constituents before and after the heating treatment. I performed single fiber pull-out tests. You can see in this video what exactly is the particular test. Here, this is the peak matrix, and this is the carbon fiber. The test is manufactured in a hot plate. I deposit some carbon fibers within very thin peak sheets, and by melting them, I create the sample, and then mounting it in the testing machine, I proceed to a tensile, let's say, test, single fiber pull-out test. You can see here that the whole thing is moving, and now you can see this was the pull-out moment. The important thing and the very difficult thing to accomplish here is that you have to actually perform a pull-out test and not break the fiber, because otherwise you get a different property. So by performing this test and acquiring the debonding load, which is the maximum load on the load displacement curve, and by measuring the exact embedded length with optical microscopy, before and after the test. You can see in this figure how the specimen was, and after the successful pull-out test, how the specimen is. By acquiring these values, you can calculate the interfacial shear strength, which is used in our case we're going to use this particular value in order to identify the effect of excessive heating in the interface properties of the material. So we want to identify through this whole analysis how much high temperature short duration processing can affect the polymer matrix, the peak matrix, the composite, the joint, and the interface properties. So a small summary. So far, a coupled thermal chemical numerical model has been developed. This model has been used to identify the optimal process window in laser heating for a top hat laser and the Gaussian laser. As I said, we know which process conditions we need for achieving high temperatures without degrading the material. Then an FTIR methodology has been developed that can be used to detect thermal degradation, thermal damage after high temperature short duration heating. And finally, single fiber pull-out tests are applied in order to assess the interface properties between the fiber and the matrix. And this methodology is going to be used for examining material samples that have not been thermally degraded and samples that have been thermally degraded. So, excuse me. As part of the future work, the investigation with the FTIR is going to take place in laser heated samples. DST analysis will take place as well to identify the effect of laser heating on the crystallinity of the material. And nanoindentation will be used in order to assess the effect of the laser heating on the mechanical properties of the material. Finally, we are going to examine the effect of excessive thermal degradation on the performance of the hybrid joint to define even more clearly what are the thermal limits of how much degradation can we accept and the joint not to be damaged, let's say, can be used. And finally, the interface properties of carbon fiber peak are going to be examined after the effect of excessive heating. Thank you very much for your attention. I would like to thank a lot my supervisors, Dr. Chris Voller and Dr. Michalis Kazilas, for all their support. I will be very happy to answer any questions if you have any. Thanks.
Okay, thank you, Dimitrios. I cannot see any question in the Q&A box. So a quick question from my side would be, you used Abacus for thermal analysis of your composite treatment, right?
Yes.
And then you said that you implemented a model for peak. Can you elaborate on that very quickly, briefly?
Yeah, I can't really hear you clearly. What I did is that I used some subroutines in order to be able to, with the temperature from the Abacus solver, to be able to calculate the degradation degree. This happens by implementing in the model with head-val subroutine the activation energy, the exponential factor, and the reaction order. And then I use this value as a state variable in order to model the material properties to be dependent on this particular value. So this value takes the values between 0 and 1. So 0 is the virgin material, the material that is in room temperature. 1 is the destroyed burnt material. So that's how the material properties develop throughout this model.
Okay. Okay, thank you. Thank you very much for your talk. Our next presenter is Bowei. He is also a PhD student at Brunel University, London, third year. His project is about laser riveting. So please, Bowei.
Hi, I just shared my screen. So I assume you can see my screen now. Okay.
Yeah, you can see your screen.
Good. Okay. So I will start it. Good afternoon, everyone. My name is Bowei Li, a third-year PhD student from Brunel University. And today my presentation topic is laser riveting, an innovative technique for dissimilar material joining. So as we know, the composite is a promising material with a lightweight but has a high strength property. So it is widely used in the aerospace application. And in this picture, for this example, the Boeing 787 aircraft, its body consists of half composite and other half is aluminium, steel, and titanium. So the question is, how could we join them together properly? Currently, there are two main methods. One is mechanical fastening and another is adhesive bonding, but they still have a few limitations. For the mechanical fastening, like bolting and riveting, the pin will penetrate through all the substrate and sheet, which is unexpected in the load-bearing structure. And as for the adhesive bonding, it needs time and for the surface pretreatment, and also have the limitation like the temperature and humidity. So the laser riveting is invited to get a fast process and with fewer limitations, and also it can keep an intact metal substrate. And this picture shows the concept of the laser riveting. From this order, at first we drill the holes on the upper sheet and put it on the joining area, then feed the wire into the hole, release the beam on it to melt it. After it's solidified, it will form a rivet cap to interlock these two sheets. And move to the experimental part here. And this is a typical laser metal wire deposition system. It consists of a laser head mounted on a 3-axis motion system and a wire feeder connect to the driving unit. And for the titanium processing, we also need a shielding device to protect the melting pole. And at the beginning, a feasibility test was conducted to build up a cylinder deposition layer by layer. And for each layer, here is a track sketch to demonstrate that the beam and wire feeding will start from this point to the whole circle deposition path. And at this end point, retract the wire. But then we add another scanning laser scanning path called wash path to make it flatter. And so we can see here is the initial result for the single circle colliding as a multiple layer deposition. Actually, this is four layer deposition. We can see there is no major defect like the large cavity or cracks. So it should guarantee the basic joining strength for future application. And here, after that, the feasibility study is after the feasibility study, because the total time is a key factor in the potential industrial application. So aiming to reduce the processing time, 3 different deposition methods is designed. The first feasibility study parameter used as a normal method deposition study, and based on it, the high-speed method increase the travel speed and the wash path speed, and also decrease the cooling gap to 3 seconds. But these two methods still are additive layer manufacturing, which means it deposits material layer by layer. But the final new method use a new method, new concept for remove the wash path speed and wash path and cooling gap, which means it can start feeding from the substrate, continue depositing the material to the endpoint as the final layer. And also the travel speed was increased, called high-speed spiral deposition. And then let's say this is a recording to show the experimental of the difference. So we can see for the final method, right hand is HSS deposition method. It only takes 13 seconds to build up the 6-layer deposition. But as for the normal method, it needs 87 seconds. And also the chart demonstrates the processing time difference and the geometrical dimensions. So from the initial, we can say the total time gradually reduced to the 12 seconds to the final method is around 80% reduced. But because the balance of the wire feeding speed and the travel speed is actually the deposition height is not changed too much. It's still around 5 or 4 millimeter height. And also for their microstructure overview, this is section overview. We can see their little difference is segregation band because of the thermal history difference. But except that these 3 deposition also have no major defect observed. And after that, the HSS deposition method used to be applied into the laser riveting concept to join the aluminium to titanium and divide 2 steps. The first step is feeding the wire into the hole to build up the rivet. And after that, a high frequency laser implanted on the rivet cap to remount the material, reform the flatter height to get a better interlock. And in this result, we can see from top and side view, we can see the original rivet after post-wash. After the post-wash, it gets flatter. And in the cross-section view, also there is two big differences. One is at the crown area. The original one shows the same microstructure with laser deposition, but in the post-wash rivet, because the high temperature stay a long time at the top area, amount of primary alpha grains formed at here. And another difference is the welding condition. In the post-wash rivet, it will the material is melting to get a better welding condition and a larger welding area here. This also reflected on the mechanical properties. At the crown area, because the crowded primary grains generated at the crown area is hardens the microhardness of the post-washed rivet load. And after also a shear test was conducted for the original rivet and post-wash rivet, and also comparative blind rivet. So for the original rivet, it shows the similar maximum load with the comparative blind rivet. But after the post-wash, because the welding condition is getting better and improved, so it shows a much higher maximum strength than the original one, is almost doubled. And the laser riveting concept also explored in the composite drawing, but actually in this experiment, a ceramic wash is inserted at here. ceramic bush inside here to prevent the composite sheet touching the deposition in the process. But we still can see the oxidation, actually also the contamination at the middle of the deposition. And also we can see the fracture surface, there is some carbon fiber inside the deposition. So to avoid this, two different methods are designed. First is post-deposition. Actually, it's those pre-deposition, 2-layer pre-deposition first, and then put the carbon fiber composite on it, and then do the post-deposition again to build up. Actually, it's in total is 4-layer deposition. And another is post-scanning. First, build up a high 7-layer pre-deposition, and then remelt it. Then release the beam on the top, melt it to form a rivet cavity. So both of this method is aiming to avoid the heat transfer at the initial layers to damage the CFR pitch sheet. And here is the results. We can see the post-scanning deposition and post-deposition method also have an intact rivet. There is no contamination and oxidation happening at here. And also it shows in the shear test that this is the blue line is the original one. The failure occurs at the middle of deposition. But for the PS and PD deposition, the failure actually is occurred at the composite. So it gets a higher strength. And furthermore, an experiment of varied scanning time also implemented on the 2mm CFR pitch sheet. Increasing time also increase some a bit maximum load up to 2 kilonewton, but after 6 seconds there is not much difference after that. And this is all my presentation today. Thank you for listening.
Thank you for the interesting talk. So the questions are welcome.
Okay.
I cannot see any questions in either the chat box or Q&A box. If there is no other question, my question would be your mechanical testing. The last set of results that you showed, is it a test of the joint between your pin and the composite, or two substrates, or what is it exactly?
Sir, I'm not hearing clearly. It's a mechanical test for.
So you presented mechanical test results.
Yes. You mean for composite or the dissimilar metal joint?
So was it the last set of results? Was it the joint tested in shear, or was it?
It's a shear test actually. It's the live shear. The joint height here and the live shear is from this direction.
What is the repeatability of your tests that you've had? So how many samples have you tested to obtain the results that you presented?
Yes, for each method, I have 3 samples. Get the test, but they all show the similar results. So I just pick the random one.
Okay.
Thank you.
Thank you. Any other questions? So we would like to thank Bowei Li for this presentation and move to the next presenter. So our next presenter is Amarachi from London University, student, second year PhD from London based at TWI. Topic is laser surface texturing of polymer materials. Over to you.
Hi everyone, can you hear me clearly?
Yes.
Okay, my name is Amarachi Obilor and my research is focused on laser surface texturing of polymer materials for surface energy control. And my TWI supervisor is Dr. Andrew Wilson. My academic supervisors are Dr. Manuela Pacella and Professor Vadim Silva-Schmidt at Lavra University. I'll be starting my presentation by giving a little bit of an explanation of what laser surface texturing is, the areas of applications, the advantages of laser surface texturing in comparison to other surface modification techniques. Then I will speak a little bit about research, literature review, and then talk about my research in the laser processing approach that I'm using, a bit of experimental work that I've done, and then my ongoing and future plan. Yeah, so laser surface texturing is basically a process that uses laser to modify the surface properties of a material by altering its surface roughness without affecting the bulk mechanical properties of that material. It's applied in electronics to improve the heating and thermal conductivity of materials. It's applied in aerospace for improved coating adhesion, also in anti-icing applications. For automotive, is used to enhance the tribological performance of mechanical components that are in contact. And in my case, material processing, it is used to improve the wettability of a material or to enhance the biological response of the material, and in some cases to also improve chemical resistance. The advantages of laser surface texturing, which I would refer to as LST in most of the slides, is the fact that the process is a one-step process. So you don't need any finishing treatment to be done after you've done the laser surface texturing. And also the features that are produced are of high precision, which gives you a good surface quality. And the high speed of processing translates to a reduced processing time, which means lower cost. And this is, of course, of importance in industry where we're looking to minimize cost and maximize profit. So it is one thing to identify the capabilities or the potentials of laser surface texturing, but it is also very important to understand how a material responds to different lasers and how you can achieve this functionality of interest to you using laser surface texturing. And of course, not forgetting that environmental conditions can also affect the outcome of the process. So pulsed lasers are preferred to continuous wave lasers because laser pulses are more energetic. And also the duration of the laser pulses has some kind of influence on how the outcome of the process would be. So for longer pulses, you would have, there'll be longer interaction time between the laser and the material. So you have enough time for ionic collision, where in which case it results to temperature rise, and then you have heat transfer through the lattice of the material, leading to heat affected zones, micro cracking, and recast layers, with, and also some other surface or material defects can arise from that. So we generally prefer to use short or ultra short laser pulses in our texturing. So because of the weak interfacial bond that exists between PEEK implants and the human bone, my research is focused on improving the adhesive properties of PEEK for biomedical applications. And several factors influence the wettability of the material. Factors like surface topography, surface chemistry, contact angle, and in most cases, the surface tension of the wetting liquid also plays a part in how it spreads on a material on a solid surface. You may ask, why am I using PEEK? So apart from the industrial relevance of my work, PEEK has been used in biomedical applications because it has high strength to weight ratio, it has very good dimensional stability, it's chemically inert, and it has good thermal resistance. A bit about literature. So several works have looked into laser surface texturing, making use of different laser parameters. In one of these studies where different wavelengths were used to texture PEEK, the surface that gave the least amount of roughness was observed to have the highest weldability compared to the other wavelengths that were used. And further analysis showed that this improved weldability was as a result of the formation of polar groups on the material surface. In a different study where these similar laser parameters were used, in this case, spots were produced on the surface of PEEK, and the authors recorded an increased surface free energy and also increased adhesion of the bonded PEEK joints from lab shear tests. It was also clear that from the analysis, there were formation of some polar groups on the treated surface that gave improved weldability. However, it has been unclear from literature what the contribution of topography is to weldability control. Therefore, my research is focused on analyzing what the topographical contribution is to weldability, which I will be doing using the picoseconds laser because of the pulse duration I mentioned earlier in my presentation. I will also be exploring the use of different beam delivery methods. The one you see at the bottom left is in the case where you have the laser beam directed on the material surface without any obstruction along the beam path. The one you have on the right is where you have the collimated beam going through a beam splitter, and you have the beam split into different sub-beams and reconverged on the material surface. This process gives you flexibility in controlling the size of the features you have by varying the angle of convergence of the sub-beams. So prior to laser texturing, my PEEK sheets were cut into smaller pieces and cleaned. And then the laser parameters that were used were selected based off preliminary trials. So different textures were produced on this surface. For the line features, they were done at different angles, and for the circular features, which were a bit novel, they were formed at 2 different diameters. So the contact angle data that was generated from the job shape analyzer, which is used for estimating weldability, was plotted against the average roughness value that was obtained from the 3D Alicona pyrofluorometer. So we can see here, so for in literature, you see that water contact angle is mostly used to assess the weldability of a material. So therefore, in this first graph, we'll be looking at the orange line. And the orange broken lines here on the graph, the first graph shows you the as received material, which we'll be considering as our benchmark. And we can see that as our roughness increased, we have reduced contact angle measurement on 3 out of 5 treated surfaces. Now, we did a further analysis to find out how surface free energy can be affected by roughness. So the second graph is a plot of surface free energy against average roughness. There is no clear trend, but we can see that to the right of the as received material, which is in the light blue bar, those were the 3 samples that showed reduced contact angle from the first graph. And we now notice that one of these surfaces, which was at a roughness of 4.14 microns, that one gave a lower surface free energy compared to the as received material, which we're using as our benchmark. And from further observation, we can attribute this reduced surface free energy as to have been due to the size of the features that were produced not being wide enough to trap the water droplets. At the bottom of this screen, the features, the surfaces you see here were the ones that gave reduced contact angle with increased surface free energy values. These surfaces have the potential for the application we're looking to achieve. However, we will do further characterization tests on them and not only on these surfaces, on the other surfaces, to have a more robust analysis as to why the surfaces have behaved the way they have. So further on to my ongoing and future work plan, I will be optimizing my experimental parameters using the full factorial design of experiment. Then I will set up the direct laser interference patterning system that I mentioned earlier, carry out more laser processing, and then do some investigation of the treated surfaces using XPSS to check for surface chemistry modifications, do some contact angle measurements, surface roughness, carry out lab shear tests to check the bonding between the peak treated surfaces. Then I will do some biocompatibility assessments using in vitro cell culture tests and evaluate what the process parameters that influence the treated peak surfaces are, thereby determining what the most effective laser surface texturing approach is in creating ideal textures for peak cranial implants. Thank you very much for listening. I'm happy to take your questions now.
Thank you, Amarachi. Any questions from the audience, please? I cannot see any questions in the Q&A box or in chat. So while we're waiting for potential questions in the Q&A box, just a quick question. So you presented a quite substantial experimental program and a sort of extensive list of future plans. Can you comment on what are the specific sort of novel contributions of your project to the society relative to what is already available in the open literature?
Okay, so like I mentioned, it's in literature, there are some works that have been done on using the picosecond laser on the treatment of peak. However, these were done mostly on peak composites, not on neat peak. But my work is focused on neat peak that has no reinforcement. That's one. Also, the direct laser interference patterning system that I mentioned in literature has been used mostly on metals, and it has been for creating textures that are more hydrophobic than hydrophilic. So I'm looking to see how I can do the opposite and achieve hydrophilicity. Another aspect is the fact that I'm trying to do some biocompatibility tests. So I am looking to see how the texture orientation will influence how well these cells can adhere to the surface of peak and how that influences their orientation, their growth, and yeah, basically how the material responds when it's in the body. I don't know if that answers your questions.
Okay, yeah, thank you very much. Thank you. Okay, so thanks again for your presentation. I would suggest we move to our next speaker. It's George, a third-year PhD researcher at Sheffield Hallam University. His talk will be on investigation of influence of friction stir welding on fixed section aluminium alloys. George, you can share your screen. Again, questions are very welcome in the Q&A box or in chat.
Is that visible?
Yes, we can see your screen.
Yeah, great. Okay, well, good afternoon. My name is George Brooks. I'm a third-year PhD student at NSIRC and also at Sheffield Hallam. This presentation is on my project, which is friction stir welding in thick section aluminium alloys. So plan today is to initially start with some background to the project, start then with the aims and objectives and the techniques I'm investigating, touch on a small amount of the results that I've collected, how my project is then hopefully going to impact on industry, some concluding remarks, and some future work that I think might be beneficial. So we'll start with background. For those of you who are unaware, friction stir welding is a solid state joining process. And in its simplest form, if you could picture two pieces of material abutting and clamped together, a tool not too dissimilar to a drill bit is then plunged into the joint line. Whilst it's plunged, it is rotating. This rotation causes friction between the tool and the material, this generates heat and plasticizes the material. And then the rotation also mixes the two pieces of plasticized material together. The tool is then traversed along the joint line, and in its wake, the stirred material cools and you have your weld. So friction stir welding has been around for about 30 years now, and there is quite a wide range of research in thin section friction stir welding. However, there's quite a limited corpus of work for thick section. And this is due to various reasons, but one of the main ones is the fact that previous industrial demand was in thin section. So a paper that was released in 2018 showed that over 50% of all applications for friction stir welding were in the transportation sector, and of this 50%, 60% was in the automotive industry. And the automotive industry has a far greater want and need for thin section than it does thick section, and that's driven the research. Automotive industry typically uses friction stir welding for a wide range of applications, such as battery trays and electric cars. However, since this PhD has begun, we have seen a growing interest in thick section friction stir welding, namely in both the aerospace and the marine sectors for components including wing spars on aircraft. So there is a growing interest, but there's currently a lack of knowledge around the subject, which is where the PhD comes in. So the aim of the project was to try and develop an understanding of how friction stir welding is going to impact the mechanical properties in 50mm thick aluminium. To do this, we set up a series of objectives. The first one being we would produce 9 welds in 3 different friction stir welding techniques in 3 different aluminium alloys. These alloys were 5083, which is typically used in the marine industry, 6082 and 7050, which are both used in the aerospace industry. And the 3 techniques are actually covered in more depth in the next slide, so I'll skip over those. Once we'd produced the 9 welds, an array of microstructural and mechanical tests were undertaken, which included but weren't limited to EDX analysis, tensile and hardness testing. And then after the testing has been concluded, being able to establish how the process parameters are affecting both the microstructure and the mechanical properties was then to be see if there was a correlation between that and a relationship could be established. So if we look at the techniques investigated, starting with weld foot weld, as the name suggests, you weld about halfway through the thickness of your material from the top surface. You then machine this flat and turn it over, and you weld the second half of the thickness of your material. This is really good because it requires a very simplistic friction stir welding machine, but your manufacturing time can be quite lengthy. Conversely to this, simultaneous double-sided can reduce your manufacturing time by greater than 50% versus weld foot weld by removing both the middle processing time and also one of the welding times. However, the drawback here is that the manufacturing time, the complexity of machinery is far greater than that of the weld foot weld. Supported stationary shoulder was the third technique that we were investigating. This is more of an exploratory technique. It's typically used in thin section titanium, but we were interested to see if it would be functioning in thick section aluminium. Supported stationary shoulder uses a cylindrical full length probe. So in this instance, a 50mm long probe. The 2 shoulders don't rotate because they're stationary. So therefore all your heat is generated by the probe rather than both the probe and the shoulder. So for the next couple of slides, before I move into how my project is going to impact in industry, I'm just going to touch on some of the results I've got so far, so you can kind of see what I'm starting to gather. So we start initially with macrographs. You can see from the images on screen that we were able to weld using all 3 different techniques. But if we start off initially with the parent material, you can see that there is this through thickness variation already before we've welded it, and that's already going to impact on the mechanical properties. If we then move to the supported stationary shoulder, which is indicated with my cursor, you can see that the profile here is linear and that we're experiencing banding. And banding is a phenomenon that occurs in friction stir welding due to differences in the dislocations. If we then compare this to both the other 2 welds, you can see that the other 2 welds are both more hourglass shaped, and this is due to the shape of the tool. Weld foot weld has a more overlapping central region, and that will have an effect on the microstructure in this region, which will become evident in the next slide. But if we look more specifically at simultaneous double-sided, we can see that the 2 probes haven't really overlapped because of a skewing motion, and this has been generated by the fact that the traverse rate was higher because the energy input into the weld was higher, so we were expecting it to be able to weld faster. But what's actually happened is we've welded it faster, but the forces on the probes have grown, and this has skewed the probe slightly off center, and it's caused this hazy region, which again will have a significant impact on the microstructure. And when we look at the microstructure, what we see is that this central region is actually bimodal, and that is to say that both large and small grains are present within this region. And if you compare this to the single processed regions of any of the other welds, you can see that the grain structure here is equiaxial and refined, and that meets with what the literature suggests in thin section as well. If we focus in on this region here, which is indicated with my cursor, this is the double processed region of a weld. And as you can see here, that the grain structure has been processed twice, and therefore at this magnification, the grain structure can't actually be visibly seen. So you'd have to go to a higher magnification, meaning that the grains are significantly smaller. But what does this have? What impact does this have on the mechanical properties? Well, if we start again with the parent material, what we see is that this through thickness variation that I mentioned with the macrograph is also visible in the hardness of the material. And this correlates to a change of hardness in your material, which has an impact. So when we then weld it, we're seeing a different kind of impact, but potentially a more beneficial one because the variation through the thickness isn't necessarily as significant. So what we see with weld is that the actually the heat affected zone is only 60 millimeters wide. Given the material is 50 millimeters thick, 60 millimeter wide heat affected zone is very good. This will have a huge impact on industry because your reduction in properties is only 60 millimeters instead of potentially being, well, if you look at supported station shoulder, it's 120 millimeters. So a really narrow heat affected zone is present in the weld. We also see that with all three welds, that the lowest hardness point is actually in that interface between the stir zone, where the grain structure was, as I showed previously, it was equiaxed and it was refined, and where that meets the heat affected zone, which is a larger bimodal grain structure, with having a contrasting grain structure, and this is causing a reduction in hardness. But how is this all going to impact on industry? Well, what we've been able to show during this project is that friction stir welding is capable of welding in 50 millimeter thick in just 1 or 2 passes. So the image on the screen here, you can see that the friction stir welding has done it in 2 passes, and we've got a full penetration weld. If you compare that to the MIG weld that's at the bottom of the screen, that was a 42 pass weld. And so not only is your manufacturing time significantly longer in the MIG weld, but also you've got to consider other factors such as distortion and how that will impact the reworking costs after you've welded it. So for friction stir welding, we found that the distortion is actually very, very low. It's typically under 1 millimeter, even in 50 millimeter thick material. And this requires far less reworking than the MIG welding, which will have a far higher distortion. Another important factor, especially for industry nowadays, is energy consumption. Friction stir welding as a plasticizing solid state process doesn't use as much energy as a fusion welding process where the material is melted. This means that you're using a lot less energy, and therefore the process can be considered greener. It's also worth noting that the process doesn't use a shielding gas, and so gases such as argon or nitrogen don't escape off into the environment, and again makes the process a slightly more greener process that industry can consider using. So there are quite a few benefits for friction stir welding in thick section that I think my project is starting to show. But most importantly, for me, it's a green process, and that is probably the most important impact that we can have. So to conclude, we've been able to produce 9 welds in 3 different grades of material. Since this presentation has been published or has been submitted, mechanical and microstructural testing is actually finished. But from the results that I showed you previously, we can see that the hardness in the stir zone is retaining about 70% the hardness of the parent material, but this reduces further to 50% around the interface between the stir zone and the heat affected zone. We've also noted that the heat affected zone width is dependent on the amount of energy we're putting into the weld. So the weld had the lowest energy input and the lowest and the narrowest heat affected zone. Supported station shoulder had the most energy input and the largest heat affected zone. And the final point that I had on my conclusions was that the grain structure was equiaxed and refined, but this just meets with what literature would suggest should be occurring anyway. So what's left? Well, I'm actually currently in the write-up period of the thesis. However, what I think could be potentially beneficial additional work to the project that I haven't actually conducted would be fatigue testing, mainly as this is an aerospace property that they take very they have weighty consideration for. So that would be really beneficial. And also EBSD specifically on the interface where that equiaxed grain structure meets the heat affected zone, because this is such an interesting point, especially with tensile data as well. Thank you very much. That's me done.
Okay. Thank you, George. So we have one question in the Q&A box, and this is do you intend to consider the version of friction stir welding with material addition?
Do you mean where you add a filler wire? Because that would be typical. Yeah, so that would be more based on the geometry of the weld. So for the work that I've been doing, I've just been doing square butt welds where you don't need any additional material. But if you were to do something such as a corner weld using friction stir, I think we have shown previously that you can use a filler wire in addition, or you can do it without a filler wire. It still performs the weld to a decent enough grade.
Okay. Thank you. Another question is, this is purely experiments-based program or project. Have you considered using simulation tools to support the design of your welds?
Yeah, so it was when the kind of methodology was being written up initially, I had this discussion with my supervisors, and we came to the conclusion that simulation in friction stir welding, although it can be done, it's not as reliable versus an actual weld as we might like, and that's not due to the simulation. That's just based on the flow of the material within the welding when it actually happens is very unpredictable. As I've been able to show in welds that I've not presented here today, I've actually had to change the direction of the tool from clockwise to anti-clockwise in order to form a consolidated weld without voids. And this has meant that the material flow isn't moving how we would expect it to. So I don't think that would be very well simulated. So I did consider it, but I've not pursued it during this project.
Okay. Thank you, George, for the interesting presentation. This presentation concludes and Q&A session concludes this session on joining technologies. Thank you very much to all attendees. And basically, we can suggest people to move to the session A, or?
I think there's just one more presentation to go in session A. So by all means, if you'd like to move to session A, then use the link that you registered with, and that'll take you over there. But otherwise, I just want to say thank you very much, Nana, for chairing the session. Thank you to our speakers as well. All brilliant presentations. And also just a reminder to our audience, if you'd like to get in touch with any of our presenters, but you didn't manage to catch their email address on the slides, you can always send us an email at inquiries@nsirc.co.uk, and we'll pass that on to the relevant presenter. Also to remind you that our first year PhD student posters and MSc posters are still on our website. So if you've got time, if you could pop over and take a look at their hard work, that'd be much appreciated. So just all that remains is for me to say thank you very much to everybody for attending, and we hope to see you next time. With that, I guess we'll close the session. Thank you.
Thank you all. Goodbye.
Goodbye.